Next, we look at correlation and covariance matrices of the transformation. But before we do that, we have to remember some results from linear algebra. Uh, Essentially, if you have two compatible matrices, compatible in the sense that you can multiply them in this way, so that the number of columns of A equals the number of rows of B. When this is satisfied, the transpose of their product can be written in this way. The product of their transposes, but you see the order changes. We have to be aware of this. And this will help us to write the correlation and covariance matrices of random vector y, uh, defined as distance transformation. The correlation matrix, of course, is defined by the expectation of this product y times its transpose. And instead of y, I can put this definition a times x, okay? And a times x transpose, I can write this as x transpose a transpose, like this, okay? And now here, I have one matrix A left multiplying x, and then I also have this matrix A transpose right multiplying x transpose. So what's in between? Okay, this is a function of the random vector x, but you have uh, multiplications by scalars. Therefore, I can actually pull out the matrix A towards the left and the matrix A transpose to the right of this expression outside of the expectation due to the linearity of expectation. Therefore, what I have is A times expected value of x times x transpose times transpose of A. But this here is, by definition, the correlation matrix of random vector x. So this is what I get. The correlation matrix of y is equal to A times the correlation matrix of x times A transpose. Very similarly, you can write the covariance matrix of y. Again, just plug in the definition. This is expected value of y minus the mean vector of y times y minus the mean vector of y transposed, and then plug in a times x instead of y and arrange the terms. So I will have a times x minus mean vector of x times x minus mean vector of x transpose times a transpose, for which we again used this relationship. Okay, and then again pull out a to the left of the expression and a transpose to the right of the expression because they are constants, and what you get is this, because the middle term will have reduced to the expectation of x times the mean of x times the mean of x transpose, which is by definition the covariance matrix of x. Okay, so in general, the correlation matrix of y, where y is defined as a times x, is given by a times the correlation matrix of x times a transpose, and the covariance matrix of y is given by a times uh, covariance matrix of x times a transpose. Okay, you'll have to be careful about where you put the transpose. It's important. Uh, Sometimes when A is not square, it's evident because the matrices need to be compatible, so that you can easily see where you should put A and where you should A transpose. But when A is a square matrix, sometimes it might be confusing. Is it the first one? Is it the second one? So you need to be careful about which one has the transpose and which one doesn't. Um, At this point, I would like to point out an earlier result to you. This is not a new result, but uh, the observation is going to be informative. Let's define n independent and identically distributed Bernoulli random variables, x sub I. Okay, each x sub I here is a Bernoulli p random variable, and all of them, x1 through xn, are assumed to be independent. Now, if you remember, the mean of the Bernoulli p random variable is p, and the variance of that random variable is p times 1 minus p. At this point, we define the random variable y as the sum of these Bernoulli p random variables. Now, you should be able to tell what distribution y has at this point. What is this? You have Bernoulli p random variables, n of them, they are all independent, and you are adding them up. What's the Bernoulli random variable? It's either 1 or 0, depending on the probability p. Okay? So when you add them up, what you get is the number of successes in and trials, independent trials. So y essentially is binomial random variable with parameters n and p, right? And we actually know the statistics of this random variable. But you see, it can be expressed also as this linear transformation on random vector x. If you have the components of x as IID Bernoulli p random variables, you can define a binomial random variable y through this transformation. You see, our A matrix here is just a row vector. And when you multiply it with this random vector, which is a column vector, you get something which has dimension 1. Of course, we will have just a single random variable in this case. And when you write the expected value of y, remember, expected value of y will be equal to a times the expected value of x and the covariance matrix of y, which in this case reduces to the variance because it's dimension 1. It can be written as a times the covariance matrix of x times a transpose, right? When you put these in, you get a here. The mean vector of x here is just a column vector of p's because, well, each of them are Bernoulli p random variables, the components, and each of them has naturally the mean of p. And essentially, this matrix product is the summation of all components in this column vector, which gives you n times p as expected, which is the mean of a binomial NP random variable. Similarly, with this covariance, you get A here, A transpose here, and this is the covariance matrix. You see off diagonals are 0 because they are all independent, and along the diagonals I have P times 1 minus P, which is the variance of each x sub I, and this multiplication will give me the sum of the elements of the covariance matrix of x, which is n times p times 1 minus p, again, as expected, is equal to the variance of the binomial distribution.